Space, the final frontier, an expanse so vast and infinite that the mind can hardly comprehend its true scale. We look up at the stars, knowing that beyond our planet there are worlds, phenomena and mysteries waiting to be discovered. But what exactly is hiding in the vastness of space? What wonders, dangers and anomalies lie beyond the reach of our telescopes and probes? In this video, we're going to explore the cosmic unknown, delving into the strange and the unseen. Join us as we journey into the heart of the universe and try to uncover some of the most intriguing things that might be lurking out there, beyond our reach. Our first stop is perhaps the most fundamental mystery of space, the expansion of the universe. Imagine a loaf of raisin bread baking in the oven. As the bread rises, the raisins within it move further apart. This is analogous to what we see happening in our universe. Galaxies, like the raisins, are moving away from each other as the fabric of space-time itself expands. The further a galaxy is from us, the faster it appears to be receding. This discovery revolutionized our understanding of the cosmos. It suggested that the universe wasn't static and unchanging, as once thought, but dynamic and evolving. One of the most perplexing aspects of the expanding universe is that the rate of expansion isn't constant. In fact, it appears to be accelerating. This discovery, made in the late 1990s, came as a complete surprise to astronomers. It suggests that there's something more at play in the universe than we currently understand, a mysterious force dubbed dark energy. Dark energy is thought to be a property of space itself, a kind of anti-gravity that pushes everything apart. The expansion of the universe is a profound mystery, a puzzle that continues to challenge our understanding of the cosmos. As if dark energy wasn't enough, there's another hidden force in the universe, dark matter. While dark energy is responsible for the acceleration of the universe's expansion, dark matter is thought to account for roughly 27% of the universe's total mass and energy. That means that the stuff we see, stars, planets, galaxies, you and me, makes up a measly 5%. But here's the catch: we can't see dark matter. It doesn't interact with light the way ordinary matter does. It doesn't emit, absorb or reflect light. It's completely invisible to our telescopes. So how do we know it's even there? We infer the existence of dark matter through its gravitational effects. Astronomers have observed that galaxies rotate much faster than they should based on the visible matter they contain. It's like watching a spinning top that seems to defy gravity, on the verge of flying apart, but held together by some invisible power. Similarly, galaxies and clusters move much faster than they should, based on the visible mass of the cluster. These observations suggest that there must be some invisible form of matter providing the extra gravitational pull to hold these systems together. Dark matter. The search for dark matter is one of the most exciting frontiers in modern science. Unraveling the mystery of dark matter could revolutionize our understanding of the universe, its evolution, and perhaps even the fundamental laws of physics themselves. If there's one thing that embodies the idea of what's hiding in space, it's the black hole. These cosmic monsters are regions of space where gravity is so intense that not even light can escape. They are the ultimate hidden objects in the universe, invisible by definition but detectable through their influence on surrounding matter. Imagine a place where the very fabric of space-time is warped to its limits, where the pull of gravity is so strong that it creates a bottomless pit in the cosmos. That's a black hole. They're formed when massive stars, much larger than our sun, collapse at the end of their lives. Think of a star as a cosmic balancing act. The outward pressure from nuclear fusion in the star's core battles the inward pull of gravity. But when a massive star runs out of fuel, this delicate balance is shattered. Gravity wins the battle and the star's core collapses in on itself. This collapse can be so violent that it triggers a supernova explosion, blasting the star's outer layers into space. What's left behind is a region of unimaginable density and gravity, a black hole. Black holes come in a range of sizes. Some, called stellar mass black holes, are just a few times more massive than our Sun. Others, known as supermassive black holes, lurk at the centers of galaxies, including our own Milky Way. While we can't see black holes directly, we can detect their presence through their effects on their surroundings. Chapter 4. Exoplanets, worlds beyond our solar system. Beyond dark matter and black holes, the search for habitable planets is one of humanity's most exciting quests. Over the last few decades, we've discovered thousands of exoplanets, planets orbiting stars outside our solar system. These discoveries have revolutionized our understanding of planetary systems. For centuries, humans have gazed up at the stars and wondered, are there other worlds out there like ours? Are we alone in the vastness of space? Thanks to advances in technology, we have the tools to search for answers. One of the most successful methods for detecting exoplanets is the transit method. As the planet passes in front of its star, it blocks a tiny fraction of the star's light. This dip in brightness is detectable by sensitive telescopes. By observing these transits, astronomers can infer the presence of the planet. The discovery of exoplanets has been astonishing. We've found gas giants larger than Jupiter, rocky worlds similar in size to Earth, and everything in between. The search for life beyond Earth is a testament to our innate curiosity and our desire to explore the unknown. Chapter 5. Cosmic Microwave Background Echoes of the Big Bang. Let's turn our attention now to something a little different, the Cosmic Microwave Background, or CMB. This faint glow, detectable across the entire sky, is the residual heat left over from the Big Bang, the event that started our universe. It's a whisper from the dawn of time, a snapshot of the universe as it was just 380,000 years after the Big Bang. Imagine a universe in its infancy, a seething cauldron of energy and particles, incredibly hot and dense. At that time, the universe was opaque, like a thick fog, because light couldn't travel freely. But as the universe expanded, it cooled. Eventually, the temperature dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This transition, known as recombination, marked a pivotal moment in cosmic history. With the formation of neutral atoms, the fog lifted and the universe became transparent. Light could finally travel freely across the cosmos. The CMB is the afterglow of this transition, the ancient light that was finally allowed to stream freely through the universe. Over billions of years, this light has been stretched by the expansion of the universe, its wavelength increasing from the visible part of the electromagnetic spectrum to microwaves, which is why we detect it as a faint microwave glow today. The CMB isn't uniform, but contains tiny temperature fluctuations, variations on the order of 1 part in 100,000. These fluctuations represent the seeds of the large-scale structures we see in the universe today: galaxies, galaxy clusters, and vast cosmic voids. Chapter 6. The Fermi Paradox. Where is everybody? One of the greatest questions in the search for life beyond Earth is the Fermi Paradox. If there are billions of stars in the galaxy, each with potentially habitable planets, why haven't we found any signs of intelligent life? This question, posed by physicist Enrico Fermi in 1950, highlights the apparent contradiction between the high probability of extraterrestrial intelligence and the lack of contact with such civilizations. The Fermi Paradox is a thought-provoking puzzle with no easy answers. It forces us to confront the vastness of the universe, the immense timescales involved in the evolution of life and intelligence, and the possibility that we might be alone in the cosmos. There are numerous proposed solutions to the Fermi Paradox, each with its own set of assumptions and implications. Some suggest that intelligent life might be incredibly rare, arising only under a very specific set of circumstances that are uncommon in the universe. Perhaps the emergence of life itself is a highly improbable event, or maybe the transition from simple single-celled life to complex intelligent life is exceedingly difficult. Others propose that while life might be common in the universe, intelligent life might be prone to self-destruction. Perhaps technological civilizations inevitably develop the means to destroy themselves through warfare, environmental degradation, or some other unforeseen consequence of their own ingenuity. Another possibility is that extraterrestrial civilizations might exist, but they choose not to contact us. Perhaps they're observing us from afar, waiting for us to reach a certain level of technological or social maturity before revealing themselves. Or maybe they simply have no interest in interacting with other civilizations. The vast distances between stars also pose a significant challenge to interstellar travel and communication. Outro, the universe's enduring mysteries. In the vastness of space, mysteries abound, from the unseen forces of dark energy and dark matter to the incredible possibility of alien life hiding on distant planets. The universe is full of questions waiting for answers. As our technology advances, we may one day uncover the secrets that the cosmos holds. Until then, the mysteries of space continue to inspire and challenge us, reminding us of the endless possibilities that lie beyond our reach.